Welcome back to the wonderful world of physics. This is a review of the important concepts that are in section 6.1, 6.2, and 6.3 as we begin our study of energy, work, and power in chapter 6. Before you go through this video, you should read those three sections. So, assuming you have read those sections, let's get into it. In section 6.2, which is about work, it defines work this way. For an object moving in one dimension, the work W done on the object by a constant applied force is work equals, and it's the x component of force times displacement. When I give the equations in this video, I give the equation number as it's written in the book. So this is equation 6.1, where f of x is the component of the force in the direction of the object's motion, and delta x is the object's displacement. At the top of the screen, we have that equation again, that work equals the x component of force times displacement. Let's look at this picture down below. Let's say that the object is being displaced in the x direction, and force could be going in a variety of directions. Here it's going off at an angle. It could be going directly in the x direction. We could have a force actually that's pulling in the opposite direction. But regardless of which way the force is going, work is calculated just using the x component of force. You can see based on this diagram and some basic trigonometry that the x component of force is the magnitude of the force times the cosine of the angle between the force and displacement. So now go to the equation above the picture. Work equals force times cosine theta times displacement. And here we're calling it delta R instead of delta X because we want to more generalize it to later on be talking about X, Y, or Z directions. So we'll just call displacement delta R. So work is equal to force times delta R times cosine theta. Now let's do some basic math review of a scalar or dot product between two vectors. This is a way of multiplying two vectors that results in a scalar. So we have A dot B, which is the scalar product of vectors A and B, and it's defined as the magnitude of vector A times the magnitude of vector B times the cosine of the angle between them. A result of the dot product is this formula that you should know, that the dot product of two vectors is the product of their x components plus the product of their y components plus the product of their z components. And so let's think back. We're going to relate it to these things, that work equals F times displacement times cosine theta. And you can see how that looks a lot like equation 6.3. So what we're going to see is that work is actually the dot product of force and displacement. And here we have equation 6.5. Work is dot product, F and delta R. Before we go on, please make sure you've worked through the examples in the section. Example 6.3 is a good example of work and the scalar product. Now let's move on to section 6.3, forces that vary. We started in the last section with this equation that work is, if we're talking just one-dimensionally, the x component of the force times the displacement in the x direction. And when we think about forces that vary, now some examples are a spring. You've learned Hooke's law a few chapters ago, that the force is proportional to how much the spring has been stretched or compressed. Later on this semester, we'll see how the gravitational force is another force that varies. If you stick with us next semester, that'll be, we'll look at electric forces. Well, the chapter, this section 6.3, does a derivation that leads us to the calculus. If you have a varying force, you can't simply multiply force times displacement because force is changing. So we end up, after the derivation, with equation 6.8, which is this, that work is the integral of force dx, as you can see right here. Now, of course, if force is not changing, this is still true, but there's no need to use the calculus if the force is not changing. If force is changing, the calculus is necessary. So if work is the integral of f dx, let's think about stretching a spring. We're going to take the force and plug it in, make that substitution, so it's kx dx, and let's work through that integration. The integral of kx, you can put the k off to the side, and integrating x dx becomes 1/2 x squared. What we're left with as you go through that integral is that the work in stretching a spring is 1/2 k x2 squared minus 1/2 k x1 squared. Those limits of integration x1, x2 refer to the position where the spring started and the position where it ends. And by position, we take that to be the distance that it's been stretched from equilibrium. Now, down below, we see this shortened version. If the spring started at equilibrium and x1 is 0, then this whole second term gets wiped out. And then we can just take the shorter version and say the work done in stretching a spring from equilibrium, some distance x, is 1/2 kx squared. So we'll use this shorter version of the equation when it's being stretched from equilibrium. If it's being stretched from some non-equilibrium position, we'll use the longer version of the equation right here. By the way, this works for compression of a spring also. Let's look at an example here of the work done to stretch a spring from equilibrium. We know that work is the integral of the curve when we graph force versus displacement. And so we can think about stretching the spring from 0 to 0.7. And what is the work? And you see the force curve, and it's actually going to be the area of that triangle. Now, work equals 1/2 kx squared. I haven't explicitly told you what k is, but let's just figure it out by looking at the chart. Force, let's go somewhere up here. If it takes 80 newtons to stretch at a distance of 0.8 meters, then K is the newtons divided by meters. So 80 newtons divided by 0.8, and it's got a spring constant of 100 newtons per meter. So now knowing that, we can plug into the equation and get work equals 1/2 times the spring constant of 100 newtons per meter, times we're stretching it a displacement of 0.7 meters squared, and we get 24.5 joules. Now let's say we want to stretch it from 0.7 meters to 0.9 meters, and you can see it's going to be the area under this triangle. If you look at the picture, you can think it is the area, just geometrically, it's the area of the triangle that goes out to 0.9. So I'm highlighting around the perimeter the entire triangle that goes out to 0.9. But then we imagine someone has already done the work, taking it out to 0.7. So we delete this smaller triangle. And what we're left with is the area in blue. We're going to use this equation that work equals 1/2 kx2 squared minus 1/2 kx1 squared. So we have 1/2. We found out in the last page that K is 100 newtons per meter times 0.9 squared minus 1/2 times 100 times 0.7 squared. And we get 16 joules. Let's look at a few problems in the back of the chapter. We'll look at number 19. To push a stalled car, you apply a 470 Newton force at 17 degrees to the car's motion, doing 860 joules of work in the process. How far do you push the car? So here I've drawn a picture. We're pushing a little down on the car, making that 17-degree angle. It's given force, the angle, and work, and we want to solve for displacement. So we'll use this equation that work equals F times displacement times cosine theta. Here I've used an X instead of an R. We're going to solve for displacement. Delta X equals W over F cosine theta. We plug in those values and we get 1.9 meters. Another question, number 44. Find the effective spring constant of a DNA molecule given that it takes 6.92 times 10 to the negative 24 joules of work to compress it 4.48 nanometers. Well, we're given the work, we're given the displacement, x, and we want to find k. So we'll use the equation, and we're assuming to compress it from equilibrium. So W equals 1/2 kx squared. We solve that for k equals 2 times work divided by x squared. Make sure we have everything in MKS units. So work is in joules, that's fine. But displacement, we need that in meters. 4.48 nanometers is 4.48 times 10 to the negative 9 meters. And we get a spring constant of 6.90 times 10 to the negative 7 newtons per meter. Number 51, you pull a box 23 meters horizontally using the rope shown in the figure in the book. If the rope tension is 120 newtons and if the rope does 2,500 joules of work on the box, what angle theta does the rope make with the horizontal? So here we're given displacement, we're given force, we're given the work. We know this equation that work equals force times displacement times cosine theta. Cosine theta equals work over force displacement. We plug in those values and we get 0.90580. That's the cosine of theta. Now we take the arc sine of that and we get that theta equals 25 degrees. The last problem in this video, problem number 65. A force pointing in the x direction is given by F equals F naught times x over x naught squared, where F naught and x naught are constants and x is position. Find an expression for the work done by this force as it acts on an object moving from x equals 0 to x equals x naught. Here we have an example of a force that varies with position, so we're going to have to use the integration. Work is the integral of f dx. We put in the limits of integration. It's going from 0 to x naught. We substitute in what is the force, and it's given in the problem F naught, x over x naught squared dx. So to do this integral, let's first get all the constants out to the side of the integral. F naught and x naught squared can factor out. And we're left in the integral simply with x squared. We're going to take the integral of x squared dx with limits from 0 to x. And when we do that, we get 1/3 x cubed. So I've put the 3 out here in the green, left with x cubed from 0 to x naught, and that becomes x naught cubed. And when we simplify that expression, we get 1/3 f naught x naught. By the way, you can play with this problem in a graphing calculator, make up some values for f naught and x naught. And the force, because it's related to x squared, it looks something like this. And what we've done is we've found the area under the curve as it goes from 0 to x naught. That's the end of the section 1 through 3 in Chapter 6 Physics Review. Have a great day.